Well, greetings everybody. So here's a question right off the assignment that's a real fundamental question where I don't think the math's very hard, but I'll introduce some new concepts and formulas to you. Um, so we start with the function, as is usually the case in calculus, okay? And it says to calculate the average rate of change and the instantaneous rate of change. Now, I have on Canvas all of these definitions and formulas written out already. So first of all, with the average rate of change, here it is. We have a function, as I said, average rate of change of y with respect to x. Y is the dependent variable, x is the independent variable, on some interval, okay? Say a to b, and by this interval, what I mean is that as x ranges from being a to some other larger number b, okay, is sometimes written delta y over delta x, f of b minus f of a over b minus a. Okay, so let's kind of frame this in within that context, okay? So the way it's written here is calculate the average rate of change of y with respect to x if x is 5 and if x changes by 0.11. So that's what that delta x means, means literally the change in x, okay? So with the way I had written it over there, you could say, all right, so x is on the interval from 5 to 5.11. That's interval notation. Or you could write with inequalities and have it say the same thing. Okay. The point is, if you're going to calculate the rate of change of y with respect to x, there has to be some change you're working with, and that's given by this delta x and this initial value of x, or this interval, or like all those different ways are just different ways of telling you, okay, so there's change happening, and here's what starts it, okay? Now, of course, if y is connected to x by some function, if the x changes, that's going to cause the y to change, and the average rate of change allows us to explore that a little bit, okay? So here goes. I'll calculate like this. What the math you see here is according to that formula that I gave over here and according to this function given in the question. Okay, so delta y over delta x is f of 5.11 minus f of 5 over 5.11 minus 5. And all that is on top, when you subtract, that's how much the y has changed as a result of the x having changed by this much. The subtraction calculates the changes. So you get the change in y over the change in x. With our function, it's going to be like this. Calculating that down and doing a little rounding, I'll get negative 0.039. Okay, so there's our answer. That's what would go in this box, right? Just asking for that number, which is the rate of change. But I might say, like, why do we say with of y with respect to x? Or how do you think about that number? I think so often in calculus, it's more important to understand what the answer means than be able to get the answer. I'm not saying you don't need to know how to get the answer, but if you get some number that's the answer, they tell me, okay, what's the significance of that number? How would you think about what it means, and so on. Here's how we think about it. That is the proportion of change between y and x. If x changes, that's going to cause y to change. And here's how. So I'll turn this into a fraction because a rate of change is change in one thing over change in another. So here's how the x and y change together. That's a 1 under there, if you want it to be a 1. It says if x increases by 1 unit, then that will cause the y to decrease by 0.039 units. That's the significance of that negative right there. So the x increases by 1, it's going to cause the y to decrease by 0.039. That's why we say the rate of change of y with respect to x. They're changing together. It's not just that they change, it's that they change together, and we want to quantify how. That's what the number does. So suppose that that's the way I have you think about that. Would you say that y is very sensitive to changes in x? I wouldn't say so. I mean, if x increased by 1 unit, then y will decrease by way less than that. Way less than that. Okay, so my impression of that number and its meaning is that y wouldn't, at least in this case, is not sensitive to change in x if x is 5 and if it changes by a small amount. Now, if we didn't start at 5, then this could be different, okay? And if x didn't change by a small amount, then again, that could like greatly alter what's happening. All right, but as it is, that's how I think about that. Now, you've seen this before, all right? All that average rate of change is, delta y over delta x, it's just rise over run or slope, exactly the way you learned it in algebra. You might not recognize it that way, but that's all it is, okay? And if you think about it like that, then that means this curve is nearly horizontal at the point where x is 5, okay? Why do I say nearly horizontal? Well, for a line that's horizontal, x can change all at once, but the y is not going to change at all. That's what makes it flat. And so horizontal lines have a slope of 0, and this number is pretty close to 0. It's very small. Okay, it's not 0, and the curve isn't horizontal there, but it's getting there. It's mostly horizontal, I'd say. It might be hard to tell the difference between this curve at x is equal to 5 and a horizontal line. Okay, so I have done part A, and I have talked about what that number means. So you're getting both sides of it. You can get the number, and then hopefully you can think a little bit about what that number means. Now, the next part says calculate the instantaneous rate of change of y with respect to x if x is 5. So, well, what is that? Is that something different? Well, say you start with the function the same way as with the average rate of change. The instantaneous rate of change is just another term for the derivative, okay? We can calculate it with the rules we already know for the derivative. We're just calling it something different, and we'll use a different notation for it sometimes, okay? That notation is called Leibniz notation. The reason why we might introduce a new notation at this point is there is a connection between these two that everybody who learns calculus should understand very well. And their notations look similar for a good reason, okay? All right, so apparently then this part B is saying what is the derivative if x is 5, okay? Rules aren't going to change. So whatever rule you would have used to calculate the derivative of this before you learn any of this new stuff is the same rules you would use now. So, all right, part B, I'll rewrite that function this way because the rules are applicable to it a little better. And then there's your derivative, -1 over x squared, okay? So the derivative of y with respect to x, or the instantaneous rate of change of y with respect to x when x is 5, is -1 over 5 squared. I'd like to get a decimal, and that's -0.04. Okay, so there's your answer to B. So when we use this Leibniz notation, dy over dx, and we want to evaluate it at a certain value of x, we often write like that. You might know there's lots of notations, different notations for the same things in math. And no different here. There are other ways you could write notation for the derivative at a certain value of x, but this is a way that we'll often do it with Leibniz notation. Okay, so I got my answers, and it seems I'm done, and then you might be happy enough with that and move on. But I did say that you should understand a lot, as much as you can, about the connection between the average and instantaneous rates of change, okay? So here they are. The average rate of change is approximately equal to the instantaneous rate of change if the change in x is small. How small might vary by situation, but I think that this will get the point across. And I think we saw it here, didn't we? It's no coincidence that these numbers are extremely close to each other. They're just off by like 1 part in 1,000. They are very close. And that change in x, it was small. Okay, so you can expect that to be true. And I think a lot about what you could understand about the derivative comes from this. So like, for example, the units of the derivative will have the same units of the average rate of change, okay? I can think of the derivative as basically telling me how y and x change together, just like here. Like that number right there told me if x increases by 1, then y will decrease by 0.039. Okay, so I could think of the derivative as telling me basically the same thing. All right, that's how I can understand that number. Now, that's the first point that I want to tell you about how these are connected, why their notations are similar for that reason. One more thing, if that original function happened to be linear, meaning its graph is a line, then the derivative and the average rate of change will always be equal. Okay, so there you go. Now we're not, so are we surprised that those were so close? Are we surprised that the average rate of change was negative 0.039 and the instantaneous rate of change or the derivative was negative 0.04? We are not surprised at that. That's how we would expect it to work out. And if I ever struggled to understand a derivative, I could think about it like an average rate of change. Okay, so reason for that, I did say calculus students should know quite a lot about this, is the derivative is just the limit as delta x goes to 0 of the average rate of change. That's all it is. Maybe you remember learning this already. We use different notation, but for the first test, I told you that the derivative was this. The limit as h goes to 0, f of x plus h minus f of x over h. Okay? At the time, we called it the slope of the curve or the derivative, but that is exactly the same thing as this, just dressed up a little bit differently. Right? That's the change in y. Down there would be the change in x, and you let the change in x go to 0. Okay? So yes, that's the reason why we would expect these two things to be approximately equal and why we can understand derivatives in terms of average rates of change if it would help us. Okay. All right, so they're all the same thing. We're coming full circle to what we learned on the first test when the derivative was first introduced as the slope of the curve. All right. So yes, we're using new notation this time. And but that's not going to change the rules. We might call the derivative something else, okay, but that's not going to change the rules. Coming up, some of our questions with derivatives might require you to express what the units are. So suppose you were struggling with what are the units of measurement for a derivative. My answer would be, well, since it comes from the average rate of change, its units are whatever the units of y are supposed to be over whatever the units of x are supposed to be. Okay, and that's how you know. All right, so that is, as long as this video may have been still kind of a crash course in this, there's still a lot more for us to look at in terms of different kind of problems, some with the math being a little more technical, but still the ideas and formulas being the same.